Hello everyone, welcome to the course on microsensors and nanosensors, and we are discussing the 8th module of this course where we are covering topics like tactile sensors and pressure sensors. This is the last lecture in this module where we are going to discuss mostly about fabrication strategies to construct these pressure sensors. We have already covered the tactile sensors in the first two lectures, and in the subsequent lectures we have discussed about pressure sensors. So if I talk about the fabrication strategies to build these pressure sensors, there are not one or two methods. There are several methods, there are several fabrication strategies to develop these pressure sensors. Some of them are like bulk micro machining of silicon. Then you have surface micro machining. You can also achieve it by surface micro machining. There are certain soft lithography techniques and different printing techniques, particularly with the wearable devices. These techniques has become very popular. Some devices has also been reported fabricated with 3D printing, and some hybrid techniques also exist where you utilize CMOS and MEMS fabrication strategy. So this is basically a integration of CMOS and MEMS based fabrication strategy. So what we will do is we will see some practical examples of some pressure sensors, and we'll see that how these systems are built up. Okay, we have done that in case of our discussion on force sensors. Okay, so let us discuss one of the technique to fabricate a silicon based pressure sensor, where the starting material is, for example, a silicon wafer of 100 orientation, which is doped by say some n-type material. So I'm using a n-type 100 silicon wafer. If you are not aware that what I'm talking about, what is this 100 wafer and all, please note that all these silicon wafers on which these devices are fabricated, okay, comes in various orientation. So this orientation means basically the Miller indices. So basically, if say for example, say these are planes in the silicon crystal, okay, and it is I'm calling it say z axis, x axis and y axis. Okay. So basically it is making say intercept of say 3, 3 and 1. Okay. These are the intercept at the 3 axes, and the reciprocal of this intercepts are say 1 by 3, 1 and 1 by 3. So the Miller indices are usually formed by just multiplying this with 3, and the Miller indices for this plane will be this system will be 1, 3, 1. Okay, so this is what I am talking about. So usually this silicon wafers come in different orientation, and depending on how it is doped, okay, you have multiple options available. Say some of the example I have shown over here, and please note that this example is valid for anything around say less than 200 dia of a silicon wafer. Okay, so usually 100 silicon wafer, which is n-type doped, have two cuts. One is this primary cut, so this is a bigger cut, and there is a smaller secondary flat. Okay, and they are at 180 degree. Okay, so this is how a typical 2-inch or 4-inch silicon wafer will look like. Okay, if it is 100 n-type, which is our case. Okay, similarly for 100 p-type, you have this primary and secondary cut at 90 degree apart. For 100 n-type wafer, you have these cuts at 45 degree. Okay, and for 111 p-type wafer, you do not have any secondary cut. Okay, you have only a primary cut. This is how we recognize a silicon wafer. If you want to know it in more detail, I will suggest that you refer some good book on fabrication technology, because these discussions are beyond the scope of this microsensors course. But I have just mentioned this because we are using a say silicon wafer of say n-type. Okay. So what I am doing is with this n-type wafer is we are fabricating piezoresistors with say surface impurity concentration of the order of say 10 power 18 per centimeter cube, okay, by ion implantation. Okay, so I have a silicon wafer. So I have say this is my silicon wafer. Please try to understand. Okay, and I want to fabricate a piezoresistor in this. Okay, we have discussed that silicon possesses the piezoresistivity property. Okay, so usually these piezoresistors are formed, okay, by doping it, and we know that there are several techniques of doping like diffusion, ion implantation and others. Okay, so what I am doing is, say I want to make a piezoresistor in this area. Okay, that's what I am showing over here. I will come back to this point. Okay, what I will do is I will localize dope this area, okay, to fabricate a piezoresistor, and the concentration of this doping is around 10 power 18 for example. Okay, usually it is 3 or 4 into 10 power 18. Okay, and this I am taking as say I am implanting a boron ion. Okay, so what I am essentially trying to do is I want to create a cavity, okay, which is, if you remember, for pressure sensor you need two things. One is a surface where the pressure will be applied. Okay, basically we have seen this in the case of absolute pressure sensor, that we need a cavity. Okay, and there we need one transducer which can convert this pressure to electrical signal. Okay, so what we are trying to do is, you know, if you see this, I have taken two wafers, a silicon constant wafer which will be static, okay, and then I have a silicon sensing wafer, and I have etched out this particular area out of it. Okay, and I am calling it, say I have used say plasma etching for this purpose. I am calling it plasma etched depression. This is a industry term. Okay, plasma etched depression. This area has been etched out, or the silicon has been etched out. Okay, so these surfaces are known as hydrated surfaces, and they are used to make certain bonding, because you have to fuse them together to make this area sealed cavity. Okay, so then you do a lot of grounding and polishing. Okay, and then you have this, since I am talking about the forming piezoresistors, basically these piezoresistors are formed in the sensing area or in the silicon sensing wafer, because this silicon constant wafer will be intact. Okay, now what I have done is I have fused these two silicon wafers together. So these are known as fused interfaces, and this area is known as sealed reference cavity, which is required, if you remember, for the pressure detection. Okay, and then you have two piezoresistors which is formed by ion implantation. All right, so one resistor is parallel to say 100 orientation of the diaphragm, while the second one, this is R1 for example, this is R2. So R1 is parallel to the 100 orientation of the diaphragm, while the other, which is R2, is perpendicular to the 110 direction. Okay, so these directions are important because if you remember, we have seen the coefficients of piezoresistivity, pi L, pi T, pi 4. You can recall that, and you can relate that with the directions and this orientation in the silicon wafer. Okay, so however, apart from this, okay, if you want to fabricate an industry grade pressure sensor, you will need multiple things on the same diaphragm. Okay, so additional periphery components like resistors and PN junctions for multiple purposes, like for temperature compensation, are also fabricated during the same implantation process as that for the piezoresistors. Okay, so you are already doing the ion implantation. Okay, what you can also do is you can have multiple areas where you want to fabricate say PN junction. So you can have say P doping here and N doping here, for example, to create a PN junction. Similarly, you can vary the dopant concentration to create the say resistors, for example. Okay, all right. So usually if I talk about a silicon wafer, these things are mostly located at the thick rim area surrounding the diaphragm. Say if diaphragm is fabricated somewhere here, these things are fabricated at the outer area, at the thick rim area, because you do not want to disturb the diaphragm. Okay. So usually they are insensitive to pressure applied to the diaphragm. So your applied pressure is localized here and it is not disturbing this area. Okay. So you can have multiple fabrication strategies, that how you will place your resistors or temperature compensators or say PN junctions around the periphery. Okay. Then this is one of the fabrication strategy. There can be other strategies. For example, this is one of the example of pressure sensor, which is from Motorola. Okay, so this is again stress sensing method. Okay, so the piezoresistor element form the strain gauges, which is formed by the ion implantation process in this silicon diaphragm. Okay, you can see that this is the H diaphragm boundary, this one. Okay, and this configuration is shown over here. This is the same configuration here. Okay, these points are 1. So this is 1. If you translate this to here, okay, this is 1, this is 2, this is 3, and this is 4th point. Okay, so excitation current is passed longitudinally through this switch, which is formed by taps 1 and 3. So this 1 and 3, what you are doing is you are providing some excitation signal. Okay, in this you can see that 1 is grounded and the supply is from 3. So excitation current is passed longitudinally through this switch, which is formed by tap 1 and tap 3 of the resistor. Okay, pressure is applied perpendicular to the direction of the current flow, okay, which will stress the diaphragm. Okay, the applied stress produces a transverse electric field in the resistor. Okay, and this electric field is detected as the output voltage. The output voltage is taken from the point. So this were 1, 2, 3 and 4. 1 and 3 were used for excitation signal, and 2 and 4 is used to detect the output. So you can see that this is 2 and 4. 2 is giving plus and this is minus. So you are taking basically a voltage. Okay, and this voltage is generated by the applied stress, which is producing the transverse electric field in the resistor. Okay, in the piezoresistors. Okay, and this output voltage is can be related to the applied pressure through some equations. I am not going into that detail. Okay, the single element transverse voltage strain gauge can be considered as the mechanical analog of a Hall effect device. Okay, there also you have all these settings and you detect the current flowing or the Hall voltage. Okay, so using a single element avoid the need to precisely match the 4 stress and temperature sensitive resistors that is connected in a kind of Wheatstone bridge configuration, but it is not exactly Wheatstone bridge, but it is connected very similar like the Wheatstone bridge. Okay, the single element strain gauge is actually electrical equivalent to a bridge circuit, but please note that its balance or offset do not depend on the match resistors. So there you have conditions like R1, R2 equal to R3 by R4, and you say that it is a balance condition. So its balance do not depend on the match resistors as it would have been in the conventional Wheatstone bridge, but it depend on how well the transverse voltage taps are aligned. Okay, how you are collecting this voltage that is being generated by the electric field. Okay, so little variation in the transverse electric field will give you the output voltage, and this is the condition of not balance condition, that there you are getting the output. Okay, when there is a pressure, there is a transverse electric field, the piezoresistor detect it and you get the output. Okay, initially it was in the balance condition and output was 0. Okay, so There are several other proposed methods also apart from these two for the diaphragm fabrication, because if you see, the fabrication of the diaphragm is playing very crucial role, because it gives you both the thing, the piezoresistors, the placement of the piezoresistor, as well as the surface area where you are applying the pressure. Okay, so there are other methods also for fabrication of diaphragm, and one of the method is, say, silicon fusion bonding, SFB. Okay, which is also popular among industry. So I will not go in detail of SFB, because fabrication is endless, and every industry has proposed different kind of fabrication strategy because of the copyright and other issues. Okay, in the SFB, what we do is, a single crystal silicon wafer can be reliably bonded with the near perfect interfaces without the use of intermediate layers. So you are not using intermediate layers, and single crystal silicons are fused. Okay, and that's why the name is directly silicon fusing bonding. Okay, however, if you have seen these different devices, the fabrication process is complex, because all have moving parts. Okay, and it require very controlled etching process, particularly the dry etching. Okay, and before actually reaching the etching, you need to do lot of implantation and other things. So basically, the fabrication process is a complex process in case of piezoresistive based pressure sensors. Okay, these devices, although are very sensitive, however, for low pressure they have they compromise at the sensitivity end. Okay, and also these piezoresistors, because you have done a lot of doping and other things, they have they are also susceptible to variation in resistance or in doping profiles because of the variation in the temperature, and that's why these devices are susceptible to the ambient temperature conditions. Okay, although not in low temperature regime, but at higher temperature regime. Okay, so therefore there are people has explored different other kind of pressure sensor. For example, another kind of pressure sensor which is very popular is capacitive pressure sensor. Okay, so in the capacitive pressure sensor, I have shown a basic layout of a capacitive pressure sensor. Again, this is also based on diaphragm. Okay, so this is all based on MEMS platform only. Okay, so you have this say a diaphragm, and beneath this area has been etched. This plate is known as static plate. So if I am calling this diaphragm as a plate, for the time being, this is my sensing plate. I will call this diaphragm as a sensing plate, and this as a static plate. Okay, very similar to the previous one, where you have seen that there was a sensing wafer, and another was this static wafer. Okay, or we have named it as constant wafer. Okay, right. So you have this sensing plate or diaphragm, where you apply the pressure, and this diaphragm deflect from its original position to this point. Okay, and here either you have dielectric or it can be air also. This is the rear cavity termination. Okay, and this is the insulating material. Okay, so a silicon diaphragm can be utilized in a alternative pressure to electrical output conversion method, that is we are discussing, which is the capacitive sensor. Okay, so in a capacitive pressure sensor, the displacement of this diaphragm alters the capacitance related to the reference plate. Okay, so when this plate was at this position, okay, say there was a capacitance associated with this plate, and this plate is making certain capacitance. Okay, and say this is say Ci. Okay, initial capacitance. Okay, now I have applied this pressure. Please note that this area is bulging out because this is my pressure sensitive area. Okay, so when I am applying the pressure, these two areas are, of course, this is a single piece silicon, so these areas are hinged. Okay, However, the central plate is deflecting. Okay, the central plate is deflecting, and because of that, if you see, this epsilon is changing in between as well as d is changing. Okay, so what is happening is you have another capacitance, say CF, the final capacitance. Okay, and using these two capacitances, you can come up with the equation of pressure, which is mostly nonlinear in nature. Okay, so this kind of devices is very popular for measurement of low pressures. Okay, so the complete sensor can be manufactured again from a single piece of silicon, because all this etching can be achieved in silicon. Okay, so when you are fabricating this with the single piece, what you are achieving is you are achieving the operational stability. Okay, then the diaphragm can be engineered to produce up to 25% change in the capacitance across the full measurement range. Okay, so when you have that large range, you do not have to use any external measure to digitize the process. Okay, since the changes are very large. Okay, therefore this kind of sensors is suitable for direct digitization. Okay, the complete sensor can be manufactured, as I have mentioned, using a single piece of silicon. It has multiple advantages, along with there are certain demerits also that we are going to discuss. Okay, please note that the piezoresistive based devices are optimized to have maximum stress at the edges, because the placement of piezoresistors at the edges, you cannot place the piezoresistors in the middle, because in the middle you have the diaphragm. Okay, you take any example of the piezoresistive based devices, you try to maximize or optimize the stress at the edges. However, if you have seen the capacitive sensor, what we have done is we want to maximize the stress at the center. Okay, so a capacitive diaphragm relies on the displacement of the central region, and that's why you have seen the back plate is bulging out at the center. Okay, so you may require to develop differential pressure sensor using this capacitive principle. Okay, so for differential pressure sensor, these diaphragms must be basically safeguarded against the overpressure, because you do not know that what is pressure A and what is pressure B. Okay, so by incorporating some mechanical stops near both the side of diaphragm, it can be achieved. Okay, so you are basically putting one mechanical stop near the diaphragm somewhere, say here. Okay, to stop breaking of this breakage of this diaphragm because of overpressure applied, particularly in the case of a differential pressure sensor. Okay, so because of small operational displacements in the piezoresistive diaphragm, the same protection is not quite effective. Okay, as a result, piezoresistive sensors usually have very low burst pressure limits, which is not more than 10 times than its full scale rating. Okay, however, for capacitive pressure sensor, when you place this overpressure stops, it can tolerate up to say 1000 times of the rated full scale pressure. Okay, so when you are dealing with low pressure, these things become very, very important. So for example, you are measuring say in the range of say 1 Pascal, for example. Okay, you are measuring this kind of pressure, and suddenly you feel that there is the pulse is applied of say 100 Pascal or say 1000 Pascal. Okay, your piezoresistive sensor is going to break in that case, because the burst pressure limit is not more than 10 times. So if the limit was say full scale rating was 10 Pascal, it cannot go beyond say 100 Pascal. Okay, because that is its burst limit. Okay, however, this kind of capacitive sensor can withstand overpressure, and this is very, very crucial when you are dealing with micro pressure sensors and nano pressure sensors. Okay, because even say for example in blood vessels or wherever, I mean for medical devices particularly, it becomes very important, because you do not know the nature of fluid that is you are measuring. Okay, so it is quite possible that in low pressure applications you may have relatively higher pressure pulse which can occur occasionally, okay, and in those cases this capacitive sensor become very important, okay. Another point is when you are applying very low pressure, the diaphragm reflection is very minimal, okay. Sometimes the deflection can be very small, that if you attach the strain gauges or even you embed it, you will not be getting any voltage measurement because the diaphragm has moved so less that there is no change in its piezoresistance, okay. In that case also this piezoresistive pressure sensors are not that useful, okay. So what can be the solution, okay? What can be the solution for even the piezoresistors or capacitive sensors are not useful in that cases, okay. However, capacitive pressure sensor, we have seen that it possesses some answer, particularly when you are dealing with low pressures, okay, but not all, okay. There are various limitations also associated with capacitive pressure sensor, like it is sensitive to parasitic capacitances which can arise because of the interferences from outside, okay. These devices are very complex for packaging because you have again the moving diaphragm, okay, and then packaging in a electronic packaging grade is very difficult, very similar to the other MEMS sensors, okay. Then you have temperature drift effects also in the capacitive pressure sensors, and since you have the diaphragm moving from the center, not although it is hinged at two other points with the overstops, okay, then also because of very thin diaphragm the device is very fragile, okay. So for devices or for the applications where you need to have low pressure, and you can compromise on the size of the sensor, because size of the sensor is also very important when you are dealing with the low pressure. There are certain solutions which is given by magnetic sensor, we call it VRP sensors, okay. So this can be another solution, particularly for measuring very low pressure. Magnetic sensors can be one of the solution, okay. One of the example of magnetic pressure sensors are variable reluctance pressure sensor, which utilizes a magnetically conductive diaphragm to alter the magnetic reluctance of a differential transformer, okay. So the combination of a E-shaped core and coil creates a magnetic flux this is one of the example of VRP sensor, okay. So the combination of this E-shaped core and this coil is creating a flux here, okay. So with field line which is passing through the core, this is passing through the core, this is also passing through the air gap, this is the air gap I am talking about, and this is the diaphragm, okay. This is the diaphragm, okay. So what I have in the form of VRP sensor, I have a core, a coil which is making a magnetic flux, okay. The field line which is being created also passes through this air gap and the diaphragm, okay. The permeability of the E core, this material, okay, this is a magnetic material which has permeability at least 1000 times higher than of the air gap, okay. So these materials have permeability as high as 1000 times of the air gap, okay. However, its magnetic resistance is lower than that of resistance of the air, okay. So the magnetic resistance of this is of the material is lower, however its permeability is higher, and we are comparing it with the air gap because we are going to use this air gap very wisely to make this kind of magnetic pressure sensor, okay, in the form of VRP sensor, okay. As the magnetic resistance of the air gap is much higher as compared to the core material, the inductance of the core coil assembly is mostly determined by this air gap and not by the magnetic material, and this is the main idea behind this VRP sensor, okay. So So when the diaphragm deflects, because of the applied pressure, there can be cases that this gap will increase or decrease depending on type of pressure. Okay, so it depends on the direction of the deflection of this plate. Okay, and when this diaphragm is deflecting, like in this case, okay, the inductance of this system is changing. Okay, so basically it is decreasing. Okay, this is the equivalent model for this kind of configuration. Okay, and this inductance is changing. Okay, so based on this inductance change with respect to the applied pressure, okay, you can have this VRP pressure sensor, and that's why its name is variable reluctance pressure sensor. Okay, so there are certain limitations of this VRP pressure sensor, including the since this is based on magnetic core and flux lines are associated, so there is a high chance that it will interfere with the external magnetic field. Okay, then this devices is also non-linear in nature, very similar to the capacitive pressure sensor that we have seen. Okay, the signal conditioning of this VRP pressure sensor is quite complex. Okay, because of the association of magnetics and inductances. Okay, and it can also have temperature induced drifts. Okay, usually you want to avoid this kind of temperature induced changes, and that's why people has come up with different kind of sensors like optoelectronic pressure sensor. Okay, so this optoelectronic pressure sensors, in the optoelectronic pressure sensor, you have the concept of diaphragm again. Okay, however, pressure causes the mechanical deformation of this diaphragm. Okay, and this interaction can affect multiple things in the light process, light emission. It can be in the process of say light transmission, reflection, absorption, or in the form of interferences. Okay, so you can have a pressure sensor based on all these things, and you have devices based on intensity modulation, then interferometry. Interferometry can be of various type, like this Fabry-Perot, we call it FB interferometers, and you have Michelson interferometers. There are certain reports of pressure sensor which is based on Michelson optoelectronic pressure sensor, basis of Michelson interferometers as well. Okay, simple bracketings are very useful in designing optical fiber based optical pressure sensors. Okay, so you have multiple optoelectronic pressure sensors itself. You have fiber optic pressure sensor, interferometric pressure sensor, you have photonic crystal based pressure sensor, and if you utilize MEMS in conjugation with optics, you have micro optical pressure sensors. Okay, so of course, we will not be able to cover all of them, but let us try to understand one of the optoelectronic pressure sensor in the form of say FP pressure sensor, which is Fabry-Perot pressure sensor. So this is one of the schematic of Fabry-Perot pressure sensor, which is of course based on FP principle of measuring small displacement as shown over here. You can see that you have a silicon diaphragm. Okay, you have fabrication of this FP interferometer in this regime. Okay, and you have detection chip which is built up of several photodiodes and integrated FP filters. Okay, a pressure chip, if you see, resembles a capacitive pressure sensor, very similar to that, because you have two areas, and in between, in this area we are interested. Okay, so a pressure sensor chip resembles a capacitive pressure sensor, but substitute the capacitor with the optical cavity. So there you were having the dielectric material in between. Now you have a optical cavity. Okay, so this forms, basically this cavity forms a FP interferometer to measure the diaphragm reflection. Again you are measuring the diaphragm reflection only, but using the optical cavity. Okay, so a back-edged single crystal diaphragm on a silicon chip is coated with a thin metallic layer. Okay, while a glass plate features a metallic layer on its rear surface. Okay, I am talking about that. Okay, two spacers maintain a distance W between the glass and the silicon chip. Okay, The two metallic layers create a variable gap Fabry-Perot interferometer with distinct mirror function. This configuration also include a pressure sensitive movable mirror, okay, which is positioned on the membrane, and a stationary semi-transparent mirror is mounted on the glass plane. Okay. So, you have very similar to FP arrangement, you have this mirror arrangements. Okay. You have a detector chip as I have shown over here. Okay. The detector chip contain multiple PN junction photodiodes, particularly in this case we can see 3 different photodiodes are there. Okay. 2 of these components are coated with the integrated optical Fabry-Perot filters that have slightly different thicknesses. Okay. These 1. Okay. 2 of these components are coated with integrated optical FP filters that have slightly different thicknesses. The filters are formed as first surface silicon mirror coated with a layer of SiO2 and thin metal, say aluminum mirrors on their surfaces for reflection. Okay. The sensor operates by measuring the wavelength modulation of the reflected as well as the transmitted light. Okay. This varies with the width of the Fabry-Perot cavity, and the width is changing by the applied pressure. Okay. The cavity's reflection and transmission exhibit almost periodic behavior with respect to the inverse of wavelength, very similar to any other FP cavity. Okay. So, it varies periodically with respect to the wavelength as inverse of the wavelength, and it is also having period which is approximately equal to 1 by 2W. Okay. W was the width of it. Okay. So, the reflected light undergoes wavelength modulation because W varies linearly with the applied pressure. Okay. So, basically this kind of devices are linear in nature. Okay. And this is very crucial when you are trying to develop a linear pressure sensor. We have seen that both VRP and capacitive pressure sensors are non-linear in nature. Okay. The advantage of this kind of optoelectronic pressure sensor is they have high sensitivity and resolution. They are immune to electromagnetic interferences. Okay. These devices can operate because these are based on mirror and optical setups. They can operate in harsh ambient, high temperature conditions as well as in the explosive ambient. Okay. Therefore, it makes them suitable for remote access as well as for biomedical applications. Okay. However, there is not everything good about this optoelectronic pressure sensors. There are certain limitations also associated with them, like since you have seen that there are cavities, there are half mirrors, then you have perfect mirrors, okay, placed in the configuration, okay, that too in a silicon micro machined area. Okay. So, their alignments are very complex and the calibration is also very challenging. Okay. These devices, although are not very much susceptible to temperature change, but they also have variations with respect to the temperature, strain as well as the vibrations. Okay. And they require special skills in developing the readout systems for this optical systems. Okay. So, we have seen that all these pressure sensors, they have something, few things are good, then there are certain limitations. Depending on your application, you can choose the right pressure sensor for the intended application. Okay. So, with this we have finished this module 8, where we have covered the tactile and pressure sensor in very brief. Along with the introduction to the different topics, we have also seen certain strategies to fabricate them. I hope that the concept is clear to you. If you are facing challenges in understanding the fabrication steps, I will suggest that you have a look on basic fabrication steps for in a MEMS process. Okay, you will have MEMS literature is very rich. You will find very good books available for this MEMS fabrication, and what we have done is we have just implemented that for the sensor fabrication. Okay, so with this we are going to end this lecture. Thank you.